The math for the radiation integral from the previous lecture is a bit complicated. Fortunately, we can simplify the math for a lot of antenna applications by using the fact that we usually don't need to know the near fields right next to the antenna. Normally, we only need the far fields with the field point far away. So here we have a coordinate system. We'll put the antenna here close to the origin, and the field point will be here. The source point is something that we integrate over the antenna, represented by a current source J. And if that point R is far away, we can make some simplifying approximations. So here's what we're going to do. I'm going to expand my coordinate system a little bit, and I'm going to put the point R here, and let's say the point R prime happens to be there. Again, that's a point that ranges over the antenna. What the Green's function calls for in the radiation integral is the distance between R and R prime, the length of the line that I've just drawn. Now, we can do a little bit of trigonometry in vector notation to come up with an approximation that simplifies the far field the radiation integral when the source or the field point is far away. So the vector r hat is a unit vector that points in the direction of the field point, and the vector r prime is a vector that goes to the location of the source point, r prime. Well, it turns out that if I make a right triangle, this little piece has length r hat dot r prime, and that comes from vector notation in trigonometry. So the length r minus r prime we can approximate as r minus the length r hat dot r prime. And basically we're using the fact that far away, the upper side of this long triangle is very close to the length of the bottom side of the triangle. So now we're going to put that in the radiation integral. The Green's function part of the radiation integral becomes g of r prime is approximately equal to, in the far field, e to the minus jk, and then r minus r hat dot r prime. And we've just plugged in our trigonometric approximation for the distance r minus r prime. Now in the denominator, we're only going to use the first term of this approximation because the adjustment r hat dot r prime matters a lot in the phase, but it doesn't matter as much in the amplitude. So down here we're just going to put 4 pi r. And there's our far field approximation. We need one more ingredient, and that is there are some del operators in the radiation integral. If we apply the del operator, we get a bunch of terms that are quite complicated, but they're multiplied by 1 over r squared. So those become really small in the far field when the point r is far away and r is large. But then we have another term, which is minus jkr e to the minus jkr over 4 pi r r hat. So what that allows us to do is to replace the del operators with minus jkr r hat in the radiation integral. If we put all those pieces together, what we end up with is E of r, the field that we want at the observation point in the far field, or far from the antenna, is approximately equal to minus j omega mu 1 minus r hat dotted with everything to the right, e to the minus jkr over 4 pi r, and then the integral is e to the jk r hat dot r prime j of r prime dr prime. Now that may not look to you to be much simpler than what we had before, but it's actually quite a bit simpler. First of all, there's no del operators. We just have dot products. That makes it easier to deal with on the left side of the equation. The integral also changes in an important way. Here what we have is a variable that we're integrating that appears in an exponential, and that is very much like another integral, e to the j omega t f of t dt. What I have below is a Fourier transform in time. What we have above is a Fourier transform in space. And that is a very important idea in antenna theory. What that will allow us to do is to use our knowledge of Fourier transforms to get insight into the behavior of antennas without even doing any calculations at all. It's a really powerful and wonderful principle in antenna theory. Now, this has all been very mathematical, so we need to do an example. What we're going to do is pick a very simple current model and find the far field. Let me get rid of all of this. I'm going to redo this for the video. I'm sure there's a faster way to do this, but I'm not that quick on the draw. No pun intended. Sorry, Dr. Long. Okay, the Hertzian dipole. We start with the dipole antenna, and this has a transmission line that feeds a gap between two poles or arms. That's a dipole antenna. The current flows in here and out there when the voltage is plus minus. When the voltage alternates, this is all AC, time harmonic, the currents go the other way. Now, if we plot the actual current on these arms, it is equal to some current I naught at the input, and then it goes to zero because we have a boundary condition. The current has to go to zero at the end of the wires. And the same thing here. But we're going to make an approximation. We're going to approximate the current as a constant. This is I, and this is, we'll make this the z direction. Now the current is not constant on the wire, so this is an approximation, but it's going to make the radiation integral easier to evaluate. Now at this point, I'm going to do things slightly differently than in the notes. We'll get the same results, so everything's okay, but what I'm going to do is I'm also going to assume the antenna is small, and if we assume the antenna is really short, so the extent of the antenna is small compared to a wavelength, I can encapsulate all of this into what we call the Hertzian dipole model, also called the infinitesimal dipole model. In the Hertzian dipole model, the current is equal to I naught, the length L of the antenna, z hat, which gives us the direction of the current vertically along the wires, and then delta of R. And that is a three-dimensional delta function. That stands for delta of x, delta of y, delta of z. So if we put all this together, what we're doing is we're taking a dipole and making an approximation. We're saying the current is approximate along the, is constant along the dipole arms. It isn't really, it's an approximation. And then we're assuming the antenna is short. So here we're assuming a constant current model, then we're assuming a small or a short dipole. We put that all together and we get the current J. Now, with these delta functions in space, I know that's an unfamiliar concept. This is tricky, it's not easy. What this does, though, is it really simplifies working the far field radiation integral. And here's how that works. The electric field radiated by the Hertzian dipole, or the infinitesimal dipole, is minus j omega mu 1 minus r hat, and then an r hat dotted with everything to the right, e to the minus j k r over 4 pi r. And now we're going to work the integral. That's e to the j k r hat dot r prime, I naught L z hat delta of r prime dr prime. Now here's the beautiful thing. In the Hertzian dipole model, we have a delta function in x prime, y prime, and z prime. And those delta functions are non-zero at the origin, or r prime equals 0. If we use the shifting property of the delta function, when we evaluate the integral, the exponential becomes 1. In fact, the entire integral becomes 1, except we have to include the I naught L z hat. Everything else is represented by it just evaluates to 1. That's why the Hertzian dipole model is important, because it's so easy to work the radiation integral. Now we just have to apply the vector part and the e to the minus jkr over 4 pi r to that. We have the electric field. Now at this point we have a little bit of an issue because we have to combine spherical coordinates with rectangular coordinates. And that is a table lookup thing. I go to Wikipedia or a textbook. This table is found in many books, but we can write z hat as r hat cosine theta minus theta hat sine theta. So now I'm going to plug that in and work out the dot products. I have minus j omega mu 1 minus r hat dot I'm going to just leave out the e to the minus jkr over 4 pi r, so I don't have to keep writing it. What I'm working with now is the z hat, but that is the r hat cosine theta minus theta hat sine theta. Now the next step I could do quickly, but I'm going to take it really slow so nobody misses what's going on here. Minus j omega mu, then I have the 1, and the 1 just means repeat everything to the right. R hat cosine theta minus theta hat sine theta. Now I have a minus r hat, and here I take the r hat and I dot it with the r hat that's to the right, and that gives me 1, and then the cosine theta. And then r hat dot theta hat is 0 because those are our orthogonal vectors. Now, if you look at what happens, the leading term cancels with the last term, and in the end, I get minus j omega mu minus theta hat sine theta e to the minus jkr over 4 pi r. And I'll just write that a little differently with things moved around. Minus j omega mu e to the minus jkr over 4 pi r sine theta. I need the I not L, I forgot that. And then theta hat. I need an I not L there. And oops. And that is our expression for the electric field radiated by a Hertzian dipole in the far field approximation. Okay, now we're going to use that. We're going to use that as an antenna to understand different properties of antennas, the gain, the radiation pattern, the directivity, the radiation resistance, and so far. So this will be our key example, the Hertzian dipole, as we go through the antenna material.